Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be talking about neutralization reactions and the autoionization of water. So in this video I'm going to be talking about KW, I'm going to be talking about equilibrium with regard to the autoionization of water and things of that nature. So let's get into this. So neutralization reactions, what are they? So when you are reacting a strong acid with a strong base, what do you get? So neutralization reaction is referring to the reaction basically between an acid and a base. When you react specifically a strong acid and a strong base together, you end up with water as one of your products along with some salt. This only is true for your strong acid, strong base reactions. If you're reacting what is a weak acid or a strong base, or a weak acid with a weak base, you're not going to necessarily get water and a salt. But I'll talk about that in more of a future video. Okay, so here I want to focus on the reaction of a strong acid with a strong base. So here we have an acid plus a base, and you're going to get water and some salt. So for example, we have hydrochloric acid, and that's going to react with sodium hydroxide, and that's going to produce water. And then the salt is your sodium chloride. Here you have your sulfuric acid, H2SO4. That's going to react with your potassium hydroxide, and that's going to give you water. And your salt here is potassium sulfate. So here, what I want to point out is that this is a double displacement or double replacement reaction. And so remember when you're doing a double replacement or double displacement reaction, the inner ions go together and the outer ions go together. And so that's what I'm showing here. In this case, the acid here is not an ionic compound, but it will ionize in water, so we can treat them as ions, even though technically they're not ions. If it's aqueous solution, then they will be ions, and how much of this is going to be ions is going to depend on if it's a strong or weak acid. So here we have a strong acid. Remember, these are both strong acids. And so they're going to ionize completely in water, so they will ionize pretty much all of it. So here, so the ions that are formed on the outside come together. So you have hydrogen plus your hydroxide, one each comes together to form water. And then you get your inner ions, your potassium ion and your sulfate ion are going to come together to form your potassium sulfate salt. And so that is your neutralization reactions involving strong acid and a strong base. So now let's get into the autoionization of water and everything that falls out of that. Okay, let's talk about the autoionization of water. So the question is, why is the pH of water equal to 7? Well, this is because water self-ionizes or auto-ionizes. So here I have the equation of water. If this is pure water, then all you have are water molecules. And so the water molecules here are going to either act as an acid or a base. We saw that in an earlier video that water is amphoteric. That means that it can act as an acid or a base. And so if all you have are water molecules, then the water molecules can act as an acid or base with each other. So if this water molecule behaves or acts as an acid, it's going to donate one of its hydrogens to the other water molecule that is acting as a base. So then you get this H plus transfer, you get a hydrogen or a proton transfer from one water molecule to the other. And so this one will lose the hydrogen, and that's going to form the conjugate base, OH minus. And then this one will pick up the hydrogen, forming the conjugate acid, H3O plus. And this is your hydronium ion. And again, the hydronium ion, H3O plus, is the same as H plus as well. So they're interchangeable. So if you see H plus written, it's actually H3O plus, the hydronium ion. And so here, one of the things I want to point out is each and every time this happens in water, you're always going to have an equal amount of H3O plus and OH minus. The hydronium ion and the hydroxide ion will always be equal to each other because you're forming one each every time you get a proton transfer from one water molecule to the other. So in pure water, the number of H3O plus is always going to be equal to the concentration of OH minus. Therefore, it's neutral because you have the OH minus, the hydroxide ion, is balanced equally with the H plus, the hydronium ion, and so that is going to be neutralized, and so you get neutral water. Well, neutral water is what pH? Well, if we consider that pH is a measure of the H plus concentration, then, and we also consider that autoionization of water is reversible, right? It is a reversible process. So therefore, we have an equilibrium that's involved. So therefore, the question now is, how do we find the H plus concentration at equilibrium? Well, you use an equilibrium expression. So what's the equilibrium expression for the autoionization of water? Well, if you remember, liquids do not show up in the equilibrium expression, so we are going to ignore water. So if we remember that the equilibrium expression for KEQ is going to be the concentration of the reactants over the concentration of the products raised to their respective coefficients, the powers of their coefficients. And so this is 1 to 1. And so here we're only going to include these, which are your reactants. We don't have these, so I'm sorry, your products. Your products are going to be in there. So products over reactants. We're not going to include these in our expression. So then the equilibrium constant that we are going to call Kw, since this is the autoionization of water, we're going to call it Kw. The equilibrium constant for the autoionization of water, that's going to be equal to the concentration of H3O plus multiplied by the concentration of OH minus. And so this is our equilibrium expression. And so we want to remember that at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14. So this is our equilibrium constant at 25 degrees Celsius. Now, we plug this in. We know from the autoionization of water that both the hydronium ion and the hydroxide ion are always equal. So we could call them X. So if we plug in X here, right? So X for H3O plus, X for OH minus, X times X is X squared. If we solve for X, then X becomes 1.0 times 10 to the negative 7. And again, X is equal to H3O plus concentration, and it's equal to the OH minus concentration because they're equal. So both H3O plus and OH minus are going to have this concentration here. And so this is why it has a pH of 7 at 25 degrees Celsius. Because if you find the pH, remember finding the pH is equal to the negative log of the H plus concentration. So if this is our H plus concentration, take the negative log of that, and the pH is going to be equal to 7, which is the power that we have here. And that's why pure water has a pH of 7. And again, I want to point out that this is important. This is only true at 25 degrees. And the reason for that is because the equilibrium constant here is temperature dependent, like all equilibrium constants. So you change the temperature, you're going to change the constant, and therefore you're going to change the concentration of H plus and OH minus. But that doesn't mean that you're now going to have an acidic water or basic water, because no matter what, the number of H plus and OH minus are always going to be equal in pure water. It's just the amount of each of those you're going to have is going to be different. I'll talk more about that in just a moment. Okay, so this is what I was just saying before. So the autoionization of water is temperature dependent, which means that the Kw, or the equilibrium constant for the autoionization of water, is going to change based on that temperature. So in practice problems, you're always going to want to assume you're at 25 degrees unless you're told otherwise. Um, so one of the things you need to think about is that the pH of water is going to decrease as temperature increases. And so even though that's the case, you don't want to then go to the conclusion or conclude from that therefore water is going to have an acidic is going to be acidic because now at 40 degrees Celsius it now has a pH of 6 and therefore it's acidic and you can't drink it. Well, no, that's not the case, because you have to always keep in mind that the autoionization of water always ends up with an equal amount of H plus and OH minus. So it's the equal numbers of OH minus and H plus that make water neutral, not the pH itself. The pH is just a measure of the H plus concentration at a particular temperature, and that can change based on the temperature. So that's what you have to keep in mind. So although at different temperatures you're going to get a different pH for your water, that's only because the concentrations of your H plus are changing depending on the temperature, but so are the hydroxide ion concentrations, and they're going to be equal to each other every single time. So water stays neutral, but pH will change depending on the temperature of the water. But whatever neutral is, that number is going to change, right? So for temperatures at 25 degrees Celsius, the neutral pH is going to be 7. At other temperatures, neutral pH is going to be something different. Okay, so let's go ahead and work a practice problem. Okay, so here is our practice problem. What is the H plus concentration in an aqueous solution with a hydroxide ion? Oops, I should add an E there. Hydroxide ion concentration of 0.001 molar at 25 degrees Celsius. So we are given the hydroxide ion concentration in water, and we want to know what the hydrogen concentration, the H plus concentration, is for that same solution. So here we want to use our Kw, so we know that Kw is equal to the concentration of H plus multiplied by the concentration of OH minus, and that we know that Kw is equal to 1.0 times 10 to the negative 14 at 25 degrees Celsius. So all we need to do is plug in the values. So we have 1.0 times 10 to the negative 14 is equal to the concentration of H plus multiplied by the OH minus concentration. So this is 0.001, which is the same as 1.00 times 10. Actually, we'll just say 1 times 10 to the negative 3. And we'll put molar in there. So now all we need to do is Uh, Actually, we don't need molar in there. Molar's not going to be in there. So now all we need to do is just divide. And when we divide, we get an H plus concentration that is equal to 1 times 10 to the negative 11. And so now we can put molar there. And that's how you solve using your KW. That's it for this video. I hope you enjoyed this video. If you learned a lot from this video, then by all means, please hit that like button, like this video, share this video with your friends. Also, make sure you subscribe to my channel, hit that notification bell, and when you do, make sure you click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Ask me questions. Let me know what you think about the videos. Let me know if there's something else you want me to do. I'd love to hear from you. Thanks for joining me and have a great day.